So in this lecture, we'll be talking about asynchronous execution of instructions in a computer. So to understand asynchronous activities in a computer, we can consider the following situation. Let's say that in your 201 class, you are asked to write the code for a sorting program. And let's say that you have to sort a very large list, so this program is going to take a while to run. You will be writing your program, compiling, and then you set it to run, and you'll be running in one of the windows in your computer. But while that sorting program is running, other things are happening in your computer. Perhaps the clock is updating, perhaps there is a website that's on that is doing some kind of animation, or you are doing some other activities. The question is, how do all these activities happen? You told the computer to sort, and your sorting program contains no instructions for everything else that's happening in the computer. So we need to understand how the interaction between that sorting program and the rest of the computer happens. Similar, if you are watching a movie in your phone, for example, and you receive a message. When you did the action to watch the movie, you told the phone to play the movie. So the play the movie program, all it's doing is to play the movie. How does it happen that you got a message while watching the movie and the message show up in your screen or made your phone vibrate? Those are asynchronous events that will cause the execution of the program to go away from the program that is running, or the main program is running, and do something else. This going away and doing something else can be handled in different ways. One of the ways that we can do that is through a process called pooling. Another way to do that is through interrupts, and there is a third way that is what we call watchdog pooling. So those are some of the things that we're going to look into this lecture. So to get us started thinking about this whole situation, that there is a main activity going on that is under the control of the programmer, and something else happens, let's consider the situation that often happens in a campus where I may be teaching a lecture in a classroom in a given building on campus, and while I'm teaching this lecture, a fire may start somewhere else in the building, perhaps far away from where we are in the lecture. And the sequence of events that are going to happen is that an alarm will sound, and when the alarm sounds, we're going to have a protocol. Usually we have to leave the room, and then we have to go somewhere. Where do we go? Usually there is some designated meeting point that's where we should meet when there is an emergency in the building. So this is a normal real-life situation that we all can understand. How do we map this normal real-life situation to the execution of programs in a computer? So the lecture happening in that lecture room is the normal instruction processing. It's the instruction processing that you have been writing all along. That is, you write the code and you tell the program to run it, and that is the normal processing. The fire is an external event that happens far away from that classroom, and while the fire is starting, we in the classroom, we have no idea that there is a fire in the building. We are just going about our normal processing. But then the alarm will be an interruption that will stop we're going to stop what we're doing when we notice the alarm, because now we need to do something different that's not the normal processing. So when I perceive the alarm, the first thing that I'm going to do, I'm going to execute what we call the leave routine cycles. We need to follow the protocol that has been established that should be done in case there is an interruption. And the decision of what to do, or the steps that we take, also we get into this is a fire routine, that is to go to the meeting point in this case, is what is done by something that called the exception handler. So the exception handler is a piece of code that has been written ahead of time, that's sitting there in the computer waiting for when an interruption happens. When an interruption happens, that piece of code is executed so that the computer does what is expected of the computer when there is that interruption. So this example was an example where the event that caused the interruption was an external event. There was a fire somewhere else in the building. However, our normal activity can lead us to an exception state. For example, we may have been teaching a chemistry class, and we may have been the ones that started the fire. So in this case, the event will be an exception that's caused by the execution of the instructions in my code. An external event that something like a fire that started elsewhere in the building, that is an interruption. So the difference between an exception and interruption is that the exception happens because something that I'm doing myself, the interruption happens because of an external source. So there are several different causes for exception and interruptions. So an exception will handle internal events to the processor. For example, if I put the number 7 into the register S0 and then I try to execute a load word from that address, that is illegal in RISC-V, because whenever I do a load word, the address that I issue the load word to must be a multiple of 4, and 7 is not a multiple of 4. That exception is called an unaligned access exception, and that will be caused by my own program. Then there's nothing external causing that. Another exception could happen if I try to do a load word from the address 0. The address 0 is an address that's reserved for the operating system and cannot be accessed by a user program. So if I try to access that address, I'm going to get an exception that many of you are familiar with, that's segmentation fault. So one of the most common causes of segmentation fault when you are writing a C program, for example, is for you to have a pointer that contains the value 0, and you are trying to access that pointer. For example, at the end of a linked list, you do not check to see if the pointer is 0, and you try to access that pointer, you are trying to access the address 0 in memory, which is illegal. Interruptions will be handling external events. For example, in many of the larger computers, desktop computers that must be plugged to the wall all the time because they do not have a battery like laptops do, in those computers, if I simply unplug the plug from the wall, I have a power failure because the computer has no battery. So the computer has to turn off when the power goes off. So, but if I take the power off, the computer does not go off immediately. The computer, although it doesn't have batteries, it has capacitors that contain enough energy for the processor to execute several instructions before it's actually turned off. And that the cycle of execution of those instructions is the power failure exception. So whenever I end up having no power, I will execute that sequence of instruction, and the external event will be caused by stop supplying power to the computer. In a phone, for example, if I type or if I click something or if I swipe something, that is called an I/O input-output event. So I provide input to my device where I causing my device to do something else. So when do exceptions occur when a program is running? And so when the exception does occur, what should the processor do? So what should the processor do when an exception starts? Well, the first thing that it has to do, it needs to know where it was in the execution of the program. So it must take the address of the instruction that caused the exception and must record it somewhere, so that, and this is in case I need to report saying, this error was caused by this instruction, or in case I need to come back and continue the execution of the program. So the question is, where are you going to save that address? And the answer is that there is a special register called the User Exception Program Counter, UEPC. And that is the register where the address of the instruction that caused the exception will be stored. And the next thing that I need to do now, I need to jump to a specified address that is an address that's stored in the user trap handler base address. It's the UTVEC, UTVEC. So our UTVEC is because it's referred to the user trap vector. Registering in RISC-V. So remember, in the example of the fire, there was a specific place that I need to go to know, there was a specific routine that I need to do to leave the room. This is the address of the first instruction of that routine, the first thing that the processor needs to do when an exception occurs. And the question is, what code should be at that address? At that address, you should have the operating system code that will handle the exceptions. So what are the things that the OS, the operating system, needs to know in order to handle the exception? First of thing, it needs to know why the exception happened. So what's the reason for the exceptions? Why did the execution, the normal execution, has stopped? And the second thing that it needs to know is which instruction caused the exception. So the instruction that caused the exception, the address of that instruction will be in the UEPC. And there are two ways that I can report the reason of the exception to the operating system. One way is known as the cause register, and the other is known as the interrupt vectors. So and different processors use different mechanisms. That's why I need to understand both. So the cause register is the one in where there is a special register that will encode the reason. So the OS decodes the registers to find the reason. So there is a single register in the processor, and that register will encode for a different. They will have a number, and each number will correspond to a different reason for the exception. And all you have to do then is to read that register and decode the value that's there to find out what the exception was, what the cause was. There is a different way to do. So in the case, just one more thing for the cause register. In the case of the cause register, the exception handler will be at one address only, and whenever you have an exception, the execution is transferred to that address, and at that address we have a code that will decode the cause register to find out what the exception was. In the vector interrupts, what happened is that there is a mode bit in the UTVEC. If the mode bit is 0, then we're going to use the cause register. If the mode bit is 1, then the interrupts will be in vector mode. So for all synchronous exceptions, except that will caused by the execution of instructions, so this is the normal execution of the program leads to an exception, the program counter will receive a base field. And for interrupts, what we're going to happen is that the base field plus 4 will be to the plus 4 times the cause number. So what happens now, I take the cause number, I multiply by 4, and take the base field for the exception handler, and that's the address that I'm going to jump to. So what happens is that I have a different address to go to for each one of the different types of exceptions. So instead of doing the decoding of the cause registers to find out what was the type of exception, I'm going to be able to write a different piece of code for each type of exception, and I put those pieces of codes at the address that is given by this formula here. So for example, a user mode timer interrupt will be at the address PC given by the base plus 0x1c. So if I go to that address, I don't need to ask what was the cause of the exception. I know that what happened is that there was a timer interrupt that led me there. Next, we're going to talk about the difference between pulling and interrupt. But let me stop this recording because we are at 14 minutes, and I'll start another one.